Okay, in the lecture of last week, we have already discussed the electrical field built up by a point source. So if you have an infinitesimal point source placed in the space, you shall establish a spherically symmetric electrical field distribution around the source location. And the expression for the electrical field is Q over 4 pi epsilon r to the square. And it's as the equation suggests, it's a vector. So it has a direction pointing outward. And the dashed line here is the so-called equipotential surfaces, which are concentric spheres. 同心圆嘛，哈，同心的球面，哈 ，concentric spheres. And by integrating using the relationship that the electrical field intensity equals to the minus of the gradient of the electrical scalar potential V, then you can do the integration to find out the V, and it's convenient to select for a point source charge, it's convenient to select the constant C as 0, that is equal to placing the reference zero potential reference to a place in the infinity. So the expression for the voltage of a point source is Q over 4 pi epsilon r. So we know that it's proportional to the magnitude of the electrical charge and is inversely proportional to the distance r. And that is the expression, the expression for point source. So to make our discussion more interesting, we can look into the case of electrical dipole, which is relatively important because it's regulate it's actually regulate our everyday life. So if you are in the study of chemistry, you know that you will deal with molecules, atoms, and the molecules, you know that you have positively charged molecules and negatively charged molecules. And those molecules will experience electromagnetic force among them. So that is the very basics of our everyday life. 为什么这样讲呢？你知道，你在学过物理的话，你就知道物理有哪几种作用力？强力、弱力、电磁力跟重力嘛，当然重力最有感觉，因为你粘在地球上出不去啊。强力跟弱力的话，除非遇到宇宙大爆炸或者是核聚变、核分裂之类的，才会需要到讨论这个部分。那重要的是，那剩下来，你每天生活经验里头，你拿手敲桌子，那个是什么力？那个是电磁力啊。好，你拿你的左手捏你的右手，你觉得你左手的手上皮肤的原子分子有碰到你右手上面的皮肤上面的原子分子吗？其实没有碰到哦。那你说我怎么会感受到那个反作用力？那其实是电磁作用力哦。就是当我们刚刚看到电场作用力是什么 ？F 等于 QE 嘛，对不对 ？Electrical charge 还有你的电场，看起来好像没有很大，但是你要想象，它跟距离平方成反比，所以当你的距离缩小到很小很小的时候，其实那个反作用力就很大了。所以你今天说，你敢甚至的触碰，我有碰到你吗？其实没有啊。当然靠得很近没有错了，但是那其实是一个电磁作用力的表现，所以在很多个，所以而这个电磁作用，你这边看到的电偶极这件事情，其实就是 化学啊，还有不要说是物理了，其实是整个化学啊、药学的一些基础因为他们其实讨论的就是正负带电离子之间的带电原子、带电离子之间，不管是原子啊、分子、小分子或大分子的形态它们之间的作用力的形式Okay, so keep that in mind. So come back to our discussion about electrical dipole. So first let's review the definition for electrical dipole. So as the name suggests, it has positive charge and negative charge. And more importantly, they should be of the same charge, the same amount of charge. But one is positive and the other is negative. And the distance between them is remarked as d. The separation between positive and negative charge is d. For our convenience, let's place the positive and negative charge along the z-axis so that the field established by this electrical dipole can be expressed more well, the field, the electrical field and the potential established by this dipole pair, this charge pair, can be symmetrically distributed in this environment. 所以为了它的你在描述它几个关系的对称方面，我们把它沿着 z 轴来摆放所以你会看到它的那个建立起来的电场跟电位是长这个图右这边来分布的And we also know that the electrical field shall begins at a positive charge and eventually goes back to the negative charge. And the equal potential surfaces, the equal voltage surfaces should be what? The surfaces or the line should be perpendicular to electrical field at all times, to the direction of the electrical field at all times. 所以电场线是由正极到负极，然后呢，电压线呢，等电位面或等电压线呢，则是跟这些电场线是正交的。这个图看起来有点复杂，但是我们这个 example 可以告诉你，它可以用很简单的数学式、很简单的三角函式来表示它，所以我们来去推导它 ，OK？So let's begin our derivation. It's relatively simple because we have only two charges, a positive one and a negative one. And the positive one, say the charge is Q, and the negative one is minus Q. And using the relationship that I draw on the blackboard, you can see that the potential established by the positive charge is here. And the negative one is here. They have the same amount of charge among the positive and negative charge source. The only difference is R1 and R2 over there. What is R1 and R2? The distance from the charge to your observation point. Say P on the figure. Alright? So for the positive charge, the distance is R1. And for the negative charge, the distance is R2. Which one is longer? Well, according to this plot, R2 is a little bit longer. And what is the difference between R1 and R2? Well, the expression is R1 minus R2, or in this expression, it should be 1 over R1 minus 1 over R2 to calculate the difference between their inverted value. And this expression is exact one, or referred to as analytical one. 所以我们在数学上说这种写法的话是解析解啦，也就是说这里头没有经过任何的简化或者是趋近。不过这个解析解写起来会有一点麻烦，所以考虑我们的实际状况，也就是说你的观察点 P。通常离这一个 electrical dipole 正 Q 负 Q 有一点距离所以在这样的状况底下，其实我们是可以做一些趋近答案变得简化一点所以这一个趋近称之为 far field approximation 原场的趋近，也就是说 P 跟正 Q 负 Q 的距离有点远，所以 R1、R2， 还有这条线是什么？这条线是从原点拉到观察点 P 的线，我们称之为 R。你觉得 R1、R2 跟 R 这3条线差不多平行，当然长短还是有差啊，这边可以看得到。但等一下下一页的话，你就可以看到它的这一个趋近的这个关系式了哈。So suppose the observation point is placed as the far field, so that the 3 lines, the 3 distance, R1, R2, and R, are nearly parallel. Then we can find out the difference between the 3 lines. Say R1 can be, we know that on this figure we know that R1 is a little bit shorter than R. And what is the difference between the 2 lines? Well, you can see that can be approximated as the projection of this distance onto this direction. So that will be d over 2 cosine theta. So R1 is shorter than R by this distance, which is d over 2 times cosine theta. So as you can see from this expression. Similarly, R2 is a little bit longer than R, and the difference in the distance can be expressed as d over 2 times cosine theta. They are the same angle, theta, and it's added on top of R. So the 2, not that this double tilde signs suggest that they are approximated value which are only valid when R is much larger than D. So that the so-called far field approximation can be satisfied. So assuming that the far field condition is satisfied, then the expression of R1 over R1 minus 1 over R2 can be approximated as this, that is d cosine theta over R to the square. Okay? Now, then with this approximation, the electrical scalar potential V established by positive and negative charge together can be expressed as QD cosine theta. This theta is dependent of your observation point over 4 pi epsilon R to the square. And the denominator, 分子的部分, the denominator can be expressed as P dot AR. AR is the direction of the observation, which is the unit vector starting from the origin, pointing toward the point P, the point of observation. And P is what? P is a vector. As you can see here, AR is a vector. P is also a vector. The dot product of the two end up as QD cosine theta. P is so-called dipole moment, electrical dipole moment, 电偶极矩P 的定义是电偶极矩。这其实在那个4.1还是4.2吧，4.2里头其实应该有讲过，不过那好像被我跳掉，没有，至少我的课没有仔细讲那个材料的那个部分Well, so P can be expressed as Q times D. The amount of charge, the product of the amount of charge, and D is the distance between the two charge. And AZ is the direction, is the description of the dipole direction. So for the study of chemistry, if you have 2 atoms, one is a positive, is positively ionized, and the other is negatively ionized because the the charge itself and the separation distance between positive of a small molecule, its electrical dipole moment is relatively small. On the other hand, if you have the so-called large molecules, 高分子就是那个分子量比较大的那个化学的那种正负离子结合的那个状态的底下，它就会有比较强的那个电流积聚那这些比较强的电流积聚其实会反映在一些我们细微的一些物理现象比如说毛细现象或者是液体表面的表面张力现象所以其实电磁学跟其他学问之间，不过毕竟电磁学是所有物理现象的最基本的描述所以大家也不用排斥它了多少知道一点以后胡乱起来会比较顺OK 好 Alright, so but anyway we can memorize this expression as QD cosine theta. So you see that what is the relation of what is the distance? What is the impact of distance of V to your observation distance? Okay, let me ask in another way. Is a stand-alone electrical charge produce a stronger electrical field, or an electrical dipole can provide a stronger electrical field? Well, the answer is the former one. A stand-alone electrical charge, even though it has only the charge Q, it can produce a larger electrical field intensity. Why? Because the electrical potential produced by a single charge is proportional to distance r. So it's stronger as your observation points moves away. On the other hand, if you have an electrical dipole, one is giving you an electrical field outward, and the other one is pulling you in. So the force, the electrical force, established by positive charge and negative charge are somewhat cancel each other. So as the distance r gets larger, the impact of an electrical dipole doing those 减少 doing those very quickly, right? So it only establish some fields in its neighborhood. So its effect is not that significant as you move away from the electrical dipole. All right, but another thing that we can find out from the expression is the amount of the magnitude of the electrical dipole moment is proportional to the charge, the amount of charge, and the distance of positive and negative charge. All right. So in this slide, we have derived the expression for the electrical potential established by the electrical dipole. And we have done this pretty easily, relatively easy. You're just taking the approximation of this calculation, right? However, what is the electrical field intensity, electrical field distribution built up by this electrical potential? Well, to derive the electrical field intensity using the definition, that is, E equals to the minus of the gradient of V. So you perform gradient operation of V in, of course, in the spherical coordinate system. So you need to look at the gradient, the definition of gradient operation in the spherical coordinate system, which is listed in section 5.1. And if you do that, things like this. This is V, taking the partial derivative to rho r, and you end up with 2 over r to the cube 啊 ，r 3次方分之2了哈。And for this one, you need to take partial derivative of v to theta. So cosine theta becomes minus sine theta. So you end up with minus sine theta. And the minus sign is cancel out with the minus sign over here. So you have a plus sign in the middle. So you have QD over 4 pi epsilon r to the cube. All right? You see, the electrical field intensity is inversely proportional to r to the cube. So what is the significance of this result? The electrical field intensity built up by electrical dipole dwindles very quickly, much quicker than a standalone electrical charge. 所以从这个式子的话，你可以看到它的电偶极的所建起来的电场会相较于单一的电荷所建起来的电场，它的影响力会更快速的衰减那除了这一点以外，你会看到的事情是，假如你是单一的一个电荷的话，它所建立起来的电场是球状的均匀分布嘛但从后面这个小括弧你可以看到，它不会是球状均匀分布的所以in this process, you see that the electrical field intensity, the direction of electrical field, varies as what? As the observation point theta changes. For theta close to 0, what is the direction of theta close to 0? Well, upward. If this is the direction of the z-axis, then theta is 0 from the negative direction, 天顶negative direction. And theta starting from 0 becomes larger and larger. What is the theta right now? 90 degrees. It keeps going, keep getting larger to 180. So the range of theta variation is from 0 to 180. Cosine theta over here is 1. What is cosine theta for 90 degrees? 0. How about 180 degrees? Minus 1. How about sine theta? Sine theta is 0 upward, 1 in the horizontal direction, and 0 again in the zenith direction or negative direction. Okay. 好，往下了 negative direction。所以你会看到电场的方向线，其实随着西塔的角度是在改变的。只要是西塔等于0，也就是接近上面正上方来看的时候，那个时候的电场是只有 r 方向的分量冲着上去。那假如说西塔等于45度，比如说是这个方向好了。注意这个时候的 cosine 西塔值也不是0是多少？根号1/2嘛，所以它会有一些朝外的分量，然后它也会有什么？也会有 sin 西塔，也是等于45度的话，西塔角等于45度的话 ，sin 西塔也是根号1/2，所以它会有沿着这一点的那个下去的方向。这边请你稍微练习一下，好不好？假如是正自轴就是 x 轴，大家知道你这个时候是西塔方向嘛，对不对？好，这一个点的 AR 方向你能够画得出来？自己先想一下 ，AR 方向怎么画？这是它的 AR 方向，这比较简单了，就朝外出去了。A 西塔方向呢 ？A 西塔方向是朝哪个方向？朝西塔值越来越大的方向，所以它的 A 西塔方向是这一个方向。有没有？自己有没有想对？好，所以反过来讲，你的观测点是在这里的话，它的 AR 方向呢在这里 ，A 西塔方向呢这个。好，所以在球坐标系统里头，每一个点它的 AR 方向、A 西塔方向，甚至 A5 方向都不一样。A5 方向呢是这样过去的，这边是这样进去的。A5 叉叉，对，叉叉，哦，这是它的 A5 方向。OK， 不过在这里头，因为它是轴对称，所以我们没有 A5 的分量。Right. So this is the electrical field intensity built up by an electrical dipole pair. So as you can see here, they are somewhat complicated, but it's not that difficult to derive using the definition of electrical potential. So it's still doable. Alright, and those lines can be drawn using the, you can, if you are familiar with MATLAB, you can draw those lines yourself using the MATLAB code. And so E is the electrical field intensity lines. They are vectors starting from positive charge and end up with negative charge. And V, the voltage or equal potential line, if this is a constant value, it is referred as the equal potential surfaces, are lines that is perpendicular to the electrical field intensity line. So as you can see here, they are always perpendicular to E field. Alright, so there are the observations that I already mentioned. So let's move on to example 5.4. Suppose we have an infinitely long line charge, as we already seen in chapter 1, I guess. In chapter 1, we already deal with the electrical field established by an infinitely long charge line. So we have, so we place a line along the z-axis, and the charge line is infinitely long, so it tends from minus z to the infinite to positive z to the infinite. And we would like to know what is the electrical field established with this line charge distribution. And again, we can find a solution in terms of superposition law, that is, assuming that the line charge is an ensemble of many short line charges. Therefore, the total field established by those line charges can be expressed as the electrical field established by those point sources, such as the drawing suggests. So you divide it into many small sections, and the electrical field can be expressed, the total electrical field can be the summation or the superposition of those smaller line charges, right? So again, we use the definition of electrical potential, that is V equal to Q over 4 pi epsilon r. Now, Q is the amount of charge, R is the distance from the charge to your observation point. So for this line charge distribution, Q, the total charge in each small section, can be expressed as rho S of 0 times dz. dz is the length of this line charge. Rho sub L 0 is what? Is the line charge density, which is the uniform value along this line of, well, that's it. And R is the distance. And for this case, here we introduce the so-called zero potential reference. It's placed somewhere near the line. And of course, you may have the question is, why not place the zero potential reference to a place very, very far away? Well, that may cause some problem, because unlike the case of point source, Now we're dealing with an infinitely long line source. So the zero potential reference point is not that convenient to place at very far away. It can be placed anywhere, except for a very, very large distance, due to the nature of this geometry. 我再问一次好了。说最近这10来年大概我听到的答案都让我非常的失望。有没有听过 Bessel function 啊？有没有？没有，完全没有。这在理论上的公数，1年级的公数应该要讲到 Bessel function 啊，至少在我那个年代是啦。虽然我那个时候的1年级的公数有上了Bessel function，但我完全不知道它在干嘛。我完全不知道它要用来干嘛。即便我学完大2的电磁学1、电磁学2，老实讲我还是不知道它在干嘛。一直到我念了研究所，再被逼着看，再念一次电磁学、高等电磁学的时候，我才发现Bessel function的用途在哪里。Bessel function 的用途在于它能够提供驻坐标系统 （cylindrical coordinate system） 驻坐标系统的偏微分方程式的一般解。它的地位就像是直角坐标系统里头的 sin function、cosine function 还有什么 exponential function 就是说在直角坐标系统里头，你在处理波动方程式这类的偏微分方程式的时候，你的 general solution 一般解大概就是，假如是共振形式的能量在一个空间里头弹来弹去的，它就是 sin 跟 cosine 那假如说它是会传播的，那它的解的形式就 exponential 正的 blah 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 跟 exponential minus blah 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 但 Bessel function 我们想说Bessel function Hankel function, Bessel function of the first kind, Bessel function of the second kind, Hankel function of the first kind, Hankel function of the second kind。那个其实就是在处理驻坐标系统里头的波动方程式的一般解。那好吧，30年前的那个公式有上到 Bessel function， 然后上了一个叫 Legendre function 的。这个大概你们大概绝对不可能碰到了。我那个时候课堂上有教了，但我不知道在干嘛它是球坐标系统里头的一般解。OK， 好，没有关系啦我们大概知道有这件事情Bessel function， 你会碰到吗？不会啦，但是我们会碰到一点点皮毛啦，也就是说你会看到线坐标系统里头，假如你是一个无限长的线的那个 source 的话，它的那个产生的场会是一个 log 形式这个其实在第1章的时候，我们在推导无限长带电热线所建立起来的电场的时候，其实已经有出现那个 log 的形式的解了我们等一下会再看到 OK Alright so Okay, in this slide, suppose the zero potential reference is placed as P sub 0 over here. So the voltage difference between P and P sub 0, if this is 0, then dV can be expressed as the potential at the observation P. So according to this expression, you can notice that the electrical potential between the 2 points can be written in this fashion. Rho sub L 0 dz, that is the amount of the charge in this small section, divided by 4 pi epsilon sub 0 AP, the distance, minus rho sub 0 dz over 4 pi epsilon sub 0 AP sub 0. So that is the the difference between the two observation points. And if you observe the geometric relationship, you see AP or AP sub 0 can be expressed as the square root of z to the square times r sub 0 to the square. So you substitute the geometric description of the problem to get the distance AP and AP sub 0. Alright? Next is perform the line integral for this infinitely long line charge. Unfortunately, this thing once blows up. Why? Because the electrical potential established by this point source is proportional to the inverse of the distance, which suggests that those charges very, very far away from your observation point, the significance of those charge will become smaller and smaller. Alright, so you will still have a converged value, even though that you shall do infinite integral over the z-axis. Alright, so let's perform the integral along the z direction from minus infinity to infinity, like this. And because of the symmetry, because we play our observation point P at z equal to 0 in the middle, in the symmetrical plane of the line. So it can be written in this fashion. Alright? So you take everything that is not relevant to the integral out as those of L0 over 2 pi epsilon. And the integral is starting from z equal to 0 to infinity, and you can see that it's related to the description of dz. Alright, so how to proceed for this integration? Well, I provide you some clue. And unfortunately, we probably do not have enough time to finish up the derivation. So you should look at this description yourself at home. But all the necessary steps are listed here. Alright, so here we need to do some change of variable. Say the parameter z should be replaced with r tangent alpha, where alpha is the angle over here. Alpha is the angle over here. So here is the angle alpha sub 0. So z to the square can be replaced with r squared times tangent alpha squared. And using some relationship of trigonometry, we can have this result. That is, the dz over square root of r to the square plus z to the square can be replaced with secant alpha, the alpha. So the integration, which is originally an integration over the parameter z, is replaced with the integration of alpha, the angle. So the span of this angle is from 0 degree to 90 degree. So the limit of the integration is changed to alpha equals to 0 to pi over 2. And with some, if you look at the integration table, you will find that the integration of secant alpha d alpha becomes log of secant alpha plus tangent alpha, right? And substitute the limits to the expression of the logarithmic function. You end up with this result. And how do you end up here? How do we end up here? Oh, yeah. You just apply the r equals, z equals to infinity and z equal to 0. Okay. If z equals to infinity, it becomes, well, it becomes this, right? If z equal to 0, this thing goes away. All right, so you get a relatively simple expression for the voltage. There is minus log sub L0 over 2 pi epsilon times log of r over r sub 0. And as you can see here, the voltage is what? Is proportional to the amount of charge. Is proportional to the charge density. It's related to the distance. It's also related to the zero potential reference, the distance to the zero potential reference. And here's the problem. If you place R at infinity, so you get up with a very large number, then this thing becomes what? Log of 0. And for logarithmic function, there's no definition for logs of 0. So it becomes illegal. So that's the reason why you cannot place log, place R sub 0, the zero potential reference, in the infinity. But you can place it anyway, because we are more interested about the difference in the potential instead of the absolute value 所以其实那个零电位点可以放在任何位置可以放在任何位置因为到后面的话你会看到那个表示式其实跟 R0 可以拿掉的但反正你不能够把 R0 放在无限远处你放在无限远处它就这个log function 就爆掉了 OK Alright, so we note that the equipotential surfaces are function of log of R over R sub 0. So it becomes a constant as long as R is a constant. If your observation point is placed at a distance R, then you shall forms equipotential surfaces. And what is the geometry of those equipotential surfaces? They are cylindrical surfaces, as the plot suggests. So here's the expression for electrical potential. That is this expression. And of course, we would like to know the electrical field expression for the electrical field intensity. How to do that? Well, you take in the gradient of V in the cylindrical coordinate system and take the negative value. So if you do that, you end up with E equals to rho sub L0 over 2 pi epsilon sub 0 R, and the direction is pointing to the RAR direction, pointing outward. So as you can imagine, the electrical field intensity is pointing outward from these cylindrical surfaces. Alright? So here's the example for individual line charges. And we already have seen that problem in chapter 1. And this time the solution can be derived in a much efficient fashion. And the very last thing we would like to discuss today is the magnetic vector potential. Magnetic vector potential, which is originated from what? From an electrical current. Here, let's assume that we have a short section of electrical current, say dl, and it carries out current. The amount of current on this line is I. Then what is the magnetic flux density B? Well, in the previous session, we already derived this result. This is reversed as what? By the Sava law, right? For magnetic force. And if you take out the other currents I, end up with this relationship. And it can be compared with the Coulomb's law. If you compare the electrical field intensity with magnetic flux density, you know that they are all function of EM properties. Here you have mu, the permeability, 介质系数. In Coulomb's law, you have epsilon, the permittivity, 介电系数. And you say they are inversely proportional to the square of the distance, square. And you see that they are proportional to the source. So the B is proportional to the amount of current, I, and E is proportional to the amount of charge, Q. However, the direction of E field and H field are somewhat different. E field is established between the source, the electrical charge source, and the observation point, while magnetic flux density is not lie on the direction. It's actually in the direction of DL cross AR. So it's in a direction perpendicular to the direction from the source to the observation point. So it's somewhat different. And what we need to do today is to derive the expression for magnetic flux density. That is, at the beginning of section 5.1, we say that because divergence of B equals to 0, and divergence of this thing equals to 0 for all vectors. So we say that B can be expressed as the curl of a vector. And we refer this thing as the magnetic vector potential. All right. And according to the Biot-Savart law, according to the magnetic flux established by a short section of a current, we can identify it as this thing. You have a curl operation. And you can say that 1 over r squared. Here we identify 1 over r squared as the minus of gradient of 1 over r. And by doing this, that is, you decompose this expression as A cross gradient of phi. So compare this expression and this, you can identify that A equals to mu I dl over 4 pi, and phi is 1 over r. And this is the vector identity, that A cross gradient of phi can be replaced with phi times curl of A minus curl of phi times A. Then you substitute these two expressions in this equation, you end up with these two terms. And now that the first term, which is the curl of dl, equals to 0, because dl is a constant in the space, constant direction, constant vector in the space. So this thing goes to 0, you end up with this thing only. And voila. Okay, voila. B equals to curl of this thing. So compare this with this. You can find out the magnetic vector potential for B for a short section of electrical current is mu I dl over 4 pi r. So this is the magnetic vector potential of a very short electrical current. So the last thing is compare the magnetic vector potential and the electrical scalar potential we have here. You see, they are similar. They are function of EM property, mu and epsilon. They are inversely proportional to the distance, r over here. They are proportional to the amount of source, say I and Q. What are the difference? The difference is V is a scalar, A is a vector. The vector expression is over here, dl, the current orientation, 电流的方向, for the current orientation. Alright, so the similarity and difference can be summed up in the last 2 pages.